Hi, welcome to Rocks with Russ. This episode we're going to look at igneous rocks and what they have to tell us in their own language about their stories. All right, so igneous rocks come from fire, essentially. Really, they come from within the earth, or in one way, shape, or another. So they basically crystallize from either magma or from lava. Magma, of course, is liquid molten rock. In other words, inside the earth that's not erupted yet. Lava has erupted. So, depending on the source, it will produce a certain kind of texture. Now, that's not the only part of the story. The other part of the story is the composition. So, depending on the tectonic setting, you'll get different compositions. So, let's talk about texture first, because that's probably the most recognizable part of an igneous rock. The chemistry, the composition comes second. So, some igneous rocks are, of course, because they're extruded as lava. We can't necessarily see their minerals. They're all made up of minerals, but we don't necessarily see their minerals. So here's an example. This piece of lava flow comes from southern New Mexico, and I can look at it and I see a certain kind of texture. I see what I would call a vesicular texture, where there were lots of trapped gases at one point. Creating lots of pockets or holes in the rock. But I don't know, of course those gases are gone. I don't know what mineral it's formed from, other than to know that it's darker in color and so forth. So I would go towards the direction of a mafic rock on this one, just based on the overall kind of color, but that's getting into composition. It's very fine grained overall, right? But it has a certain kind of texture to it that is indicative of a rock that was cooled really, really fast, where the gases didn't even get a chance to be released. Another, that's one type, all right? You might call this a pyroclastic sort of thing, but it's really just the lava flow, portion of lava flow, so it's not a pyroclastic in that kind of sense, but this is obsidian. The obsidian is volcanic glass, and obsidian erupts very, very rapidly and also cools very rapidly. But it also cools under it's produced under certain conditions, and so this has been used by many people for a long time as a source rock to produce stone tools. Because when you break it, it's got that nice conchoidal fracture that's distinctive of quartz, but it also produces a very nice razor edge, and so it's been very useful for many thousands of years by humans as far as making stone tools. So these are sort of the pyroclastic variety. There are, of course, there's tuff, there's pumice, and a variety of other things like that. I might call this a scoria if I was going to be really particular about it, perhaps. But even then, it's really heavy, and scoria doesn't necessarily have to be really heavy. So there's some wiggle room in some of these. All right, so there's a pyroclastic texture, the kind of stuff that's extruded quickly out of a volcano and then cools. There's lava that cools relatively slowly, but still quickly. But where I can't see the minerals, this is all lichen on here. This is basalt from Mole Hill near Harrisonburg, Virginia. And again, I can't look in here in this rock and see the individual minerals because they're so fine-grained. And the reason they're fine-grained is because they cooled rapidly, relatively speaking. And it's all made up primarily of olivines and pyroxenes and so forth, but I can't tell because they're so small. Not without putting it through, say, an XRF or an X-ray fluorescence or something like that am I going to be able to figure out exactly what's in this rock. But sometimes you'll see phenocrysts, larger crystals that had crystallized out, that did have more time until the whole thing was cooled. We sometimes call that a porphyritic texture, where you have two different textures going on, where you have phenocryst that cooled slowly at first, and then for whatever reason the magma cooled rapidly, and then the rest of the ground mass or the matrix cooled, made small crystals. Okay, so this is basalt. Basalt is one end of what we refer to as the fine-grained texture. We also have a couple of other textures. This rock over here is not quite what we call the other side of it, but the other side of the aphanitic or fine-grained texture is the pegmatitic or super coarse mineral grains. So this granite over here came from Ontario, Canada, just north of Lake Superior, and you can see that there's minerals in here, and they're really big. Now, they're not as big as pegmatites can be, but it's an example of where we're going with that, right? So they're fairly large. This would be on the upper end, perhaps a phaneritic texture, but it's a good example of where things can go, because I would also call this granite, which is a piece of countertop, a phaneritic texture as well. I can clearly see the minerals in it, right? So there's sort of a break between phaneritic to pegmatitic somewhere in terms of the size of the typical size of the mineral grains, but we're not going to get hung up on that right now. Just the really, really, really big mineral grains are pegmatitic. All right, so there's aphanitic, fine-grained, there's phaneritic, which is coarse-grained, and then there's pegmatitic, which is super coarse-grained, and then there's pyroclastic, okay? Now, within those textures, there's different compositions, and that's where I'm getting at the tectonic setting. So tectonic setting also dictates the pyroclastic portion of things, because some volcanoes spew stuff out in huge explosions, like Mount St. Helens. Others just sort of flow things out a little less dramatically. You can go to Kilauea. It still looks dramatic to watch it, but it's, as far as volcanoes go, you can go and watch it from a certain distance and not get hurt. And so some Icelandic eruptions are like that as well. That's because the magma is mostly mafic in texture and composition, and it's so because of that it has less water vapor, which makes it much less explosive, and it has less silica in it, which makes the magma less thick and goopy, it makes it more or less viscous rather. Okay, so the more viscous the magma is, the viscosity is determined by silica, and the more water vapor there is in the magma, the more explosive it's going to be. The more it's going to be like a plug of something that holds up for a while and then blows up after, because it's so thick and goopy. All right, so your typical example of that would be these granites, felsic magma, the other end of the composition scale from mafic. Mafic is rich in the mafic minerals of Bowen's reaction series, so the olivines, the pyroxenes, and so forth are what primarily make up, and of course there's some feldspars over there, sodium and calcium feldspar. Those minerals are what primarily make up mafic minerals, or mafic rocks. On the other end, the bottom of Bowen's reaction series, we have the felsic rocks, and those are things like these, where you have a lot of this pink mineral, orthoclase, but all of the minerals in here are silica. I mean, they're all silicates all around, but the silica content of this is much higher than it is of basalt. And so it also tends to have a lot more water vapor in it, partially because there is a lot of water in the mantle, or in the upper mantle, where some of this magma originates, but more importantly, there's water being brought down in subduction zones during the subduction process, and so these tend to be your typical subduction zone volcanoes, kind of like a Mount St. Helens or even a caldera like, say, Yellowstone, right? And so these tend to have very, very, very silica-rich magmas, and part of that is because the partial melting that's going on with the upper mantle and some of the lithosphere is incorporating more silica-rich continental rocks, continental chemistries into the rock from what may have started out as mafic. It's becoming much more enriched in silica through that process at those boundaries, and so you end up with this kind of composition. Going back to mafic, this is typical of a spreading center, an ocean spreading center, or an intraplate hotspot like Hawaii, and so forth. In between, you have the more common, most stuff is in between those two, right? So, you have like something that's more like an andesite, where you have a combination of mafic and felsic minerals, so in between the two, and so it'll look more like a black and white speckled sort of thing. And most volcanoes at subduction zones are more like an andesitic. And of course, andesitic has the word Andes in it, and Andes, the Andean range, is a subduction zone. So that sort of illustrates it for you. So again, there's a variety of compositions as well, from mafic to intermediate or andesitic to more felsic. Okay. There's also an ultramafic variety, and ultramafic rocks, I have one here, tend to be almost purely olivine. And they're sort of the deep mantle type stuff, and they have a greenish hue to them. This one's gone through some metamorphism. This is also from southern Ontario. This is actually a piece of komatiite, which is a fossil rock. Komatiite, to our knowledge, is not produced anymore on the Earth because the conditions aren't there anymore for komatiites to be produced. But back in this time, over 1 billion years ago when this rock was formed, the komatiites were being produced. So this is ultramafic. So on Bowen's reaction series, you have the ultramafics, you have the mafics, then you have the intermediates, and then you have the felsics. You also have 2 series of minerals. And if I don't have a figure in front of me, but you'll see that in class. You have the continuous series, which are the feldspars, where different ions are subbed into a feldspar structure. And then over here you have the discontinuous series. Okay, and then of course if you're going to weather these rocks, they're going to weather differently. So primarily the feldspars are weathering through hydrolysis, and the discontinuous series minerals are weathering through oxidation and things of that nature. And so there's a lot of really, really great stuff that goes on with all of these igneous rocks. So they have stories to tell, and these igneous rocks are really, really important. They tend to have really good fertile soils around volcanoes for a reason. So because there's a lot of great mineral content that plants love, and of course that we need. So igneous rocks are important for that reason, because they provide a lot of the sustenance we need for our food. But also, igneous rocks do a good job of concentrating minerals. So especially minerals that we think are very important economically: gold, silver, things of that nature, copper. Igneous environments are really good at concentrating those, and so we can find them in large ore bodies more easily because of the movement of materials around and the different processes that are going into different situations to help concentrate those minerals into ore bodies. So igneous rocks are important to us, and they're not just rocks. Every rock has a story to tell, and every igneous rock also has a story to tell. And again, hopefully you've learned something of that story. Hopefully you've gained some language, some grammar to help carry you on your next step. We'll be looking at metamorphic rocks and sedimentary rocks next. All right, until next time.